Let's jump right into this. The alien language, from algebra to quantum supremacy. When you stare down a complex math equation, what goes through your mind? For a lot of us, it kind of just looks like a daunting pile of homework you'd rather avoid. But what if we completely flip that perspective? What if we stopped seeing equations as chores and started seeing them as these absolutely thrilling puzzles just waiting to be cracked? Because math isn't just numbers scribbled on a page. It is literally the fundamental operating system of the entire universe.
Seriously, what if math is just an alien language waiting to be decoded? Well, today, we're going to crack the code of that exact language together. We're tracing a fascinating path from the building blocks of basic algebra all the way to the absolute mind-bending limits of quantum computing. By learning how to actually read this language, we get to see how physicists invent entirely new laws of nature and build machines that process data in ways that completely defy human intuition.
Think of an equation as a relationship. To read it, you've got to know the basic alphabet first. On one side, you have your variables. These are the letters acting as stand-ins for numbers that can change. You plug different numbers into them, but the equation itself decides how the other numbers have to react. On the flip side, we have constants. Now, you have to keep a really sharp eye out for constants because they often disguise themselves as variables. They're written as letters or symbols too, but they are fixed numbers that never ever change. Think of the famous number pi, or g for the gravitational constant.
Let's ground this in the real world for a second. Take Newton's law of universal gravitation. It sounds super complex, but break it down and you just find your variables, like the masses of two objects and the distance between them, and your constant, which is that tiny gravitational constant g. Once you spot those, you literally just plug in the real-world numbers. For example, if you calculate the gravitational pull between an apple and an orange as they just sit there on a table, the resulting force is incredibly tiny. It equals roughly the weight of a single grain of pollen. That's what math does. It takes abstract letters and turns them into these fascinating, tangible physical realities.
Now, the crucial thing here is that once you have your numbers, you have to follow the strict rules of the road to solve the puzzle. That's the order of operations. You always tackle anything inside brackets first. Then you move right on to multiplication and division. And a quick pro tip for reading math, anytime you see variables sitting right next to each other with absolutely no symbol in between, it automatically means they are being multiplied. Finally, you clean up with your addition and subtraction. Follow that strict hierarchy, and you decode the equation perfectly every single time.
Basic algebra is fantastic for shuffling equations around, but to invent entirely new physics, you need a way more powerful tool. There's this great quote from Domain of Science: "Like a plumber has a wrench, a physicist has calculus." Calculus is the essential everyday bread-and-butter toolkit that physicists use to derive completely new descriptions of reality. Section 1. Calculus, the physics toolkit. So why do we even need calculus in the first place? Well, when variables get squared, straight lines turn into curves, and simple geometry totally fails us. We have to rely on two inverse but incredibly complementary operations to make sense of it all. First up is integration. Imagine you're trying to find the exact area under a sweeping curve. Integration approximates that area by packing it full of rectangles. As you shrink the width of those rectangles down until they're infinitely small, your calculation becomes absolutely perfect. The second part is differentiation, which is basically the exact opposite. It calculates the gradient, or the steepness of a curve at any specific point using infinitely tiny triangles. Together, these tools let us describe exactly how certain things change when other things change, which is literally the core of all physics.
Section 2. Enter quantum computing.
Okay, we've talked about the math on paper. Now let's talk about the physical hardware actually processing the universe's data. There is a profound gap between the tech you're using right now and the tech of the future. Classical computers, like your laptop or your smartphone, they run on binary. They process information using bits that are strictly in a state of 0 or a state of 1. It's a simple, deterministic switch. But quantum computers, they use quantum bits, or qubits. A qubit can be a 0, it can be a 1, or it can exist in this special, incredibly powerful mixed state. The first wild phenomenon that gives quantum computers their seemingly magical power is superposition. This is that special intermediate state where a qubit exists as a probability of being both 0 and 1 simultaneously. Now, when you finally measure the qubit, it collapses into just one of those states based on probability. But here's the absolute genius part. Scientists can actually tune that state. They write algorithms that boost the probability of getting the correct answer and shrink the probability of getting the wrong one.
And superposition builds into an even more astonishing phenomenon: entanglement. This is the second major key to quantum power. Entanglement happens when you take several qubits and join them together so inextricably that they literally have to be treated as one single object. If you entangle just 2 qubits, they can exist in a mixed state of 4 possibilities all at once. And here's where the math just explodes. Every single time you add just one more entangled qubit, you double the number of states the system can exist in. It scales exponentially. While classical computers are stuck searching through data one by one, entangled quantum computers can process a massive, exponentially growing number of states simultaneously.
Section 3. The Quest for Supremacy.
Because quantum scaling is so aggressive, researchers everywhere, from Google to IBM, are locked in this massive race for quantum supremacy. That is the exact moment a quantum machine successfully beats the absolute best classical supercomputer at solving a highly complex problem. To prove it, they use a test called the sampling problem. Imagine having 50 qubits, all entangled together. Thanks to that exponential math we just talked about, those 50 qubits are simultaneously existing in about a quadrillion states. That's a million billion possibilities at the exact same time. When you measure it, the system naturally collapses and spits out a string of results based on its probability distribution. Doing this is perfectly natural and easy for a quantum computer. But if you ask a classical supercomputer to mathematically simulate that exact same probability distribution, it struggles immensely.
Check out this specific number, 56. Right now, 56 qubits is basically the absolute ceiling of what we can simulate classically. IBM currently holds the record for using a traditional supercomputer to successfully simulate a quantum system of this size. So, 56 qubits is the frontier. If you build a high-quality quantum computer with more than 56 qubits, classical computers simply cannot simulate it anymore. You've officially crossed into a territory where the quantum machine is doing something no classical computer ever could.
But what happens if we push that math just a little bit further? Say, to 260. If you build a quantum computer with 260 entangled qubits, and you tried to simulate it on a classical computer, well, the sheer size of the supercomputer you'd need to simulate those 260 qubits would require more traditional classical bits than there are atoms in the entire known universe. Let that sink in for a second. It is an absolutely staggering testament to the raw exponential power of quantum mathematics.
We started out by looking at basic algebra, right? Finding variables and constants just to measure the gravity on a single grain of pollen. And by following that math through the curves of calculus and right into the wild probabilities of quantum mechanics, we have arrived at machines that literally defy the limits of physical space. So I'll leave you with this. If just 260 qubits hold more computational complexity than there are atoms in the known universe, what infinite possibilities are we going to decode next?